Sorry. So I can do the next one and you do the one after, if that's all right?
That sounds fine. Thanks.
Yeah, sure. So Vivek's staying with us to give a talk on dual mode NIZK's possibility and impossibility results for property transfer.
Okay, so hi again. Now I'm going to talk about dual mode proof systems and property transfer, and this is joint work with Mihir Bellare. Let's first quickly recall non-interactive proof systems in the CRS model. So in the CRS model, there are two parties called the prover and the verifier, and there's assumed to be a trusted setup algorithm that generates a CRS and sends it to both parties. A relation is a function that takes in the CRS a statement and a witness and returns either true or false. We are interested here in NP relations and languages, and the languages we consider are CRS dependent. The prover has a statement and a witness, and the goal of the prover is to convince the verifier that the statement X is in the language. In order to do this, the prover runs the proof generation algorithm and sends a generated proof to the verifier. The verification algorithm is then used to decide whether the proof is valid or not. Various properties such as completeness are required of these proof systems. Some of the other properties include soundness, which requires it to be hard to construct a proof for a statement not in the language such that the verification algorithm accepts the statement proof pair. Extractability requires, on the other hand, that if the adversary is able to produce a valid proof for the statement, there's an extractor algorithm that can obtain the witness from the adversary's information. Witness indistinguishability says that if there are two witnesses for a statement, it is hard for an adversary to be able to tell which witness was used to generate the proof. And finally, the zero knowledge property guarantees that a proof generated for a statement in the language reveals no information about the witness for that statement. So we now look a little more at two variants of the soundness definition, depending on whether the definition is penalizing or exclusionary. This distinction was first considered by Bellare, Hofheinz, and Kiltz in 2015 in a different context. The penalty style definition makes no restrictions on the polynomial time adversary. Instead, it includes in its win condition a check of language membership for the statement in the query. This prevents the adversary from winning using a query with a statement in the language. In the exclusion style definitions, on the other hand, the adversary is restricted to almost never make queries in which the statement is not in the language. We call such adversaries membership conscious adversaries. So a membership conscious adversary will pick a statement belonging to the language with negligible probability. The win condition for the adversary here then is simply a check for whether the verification algorithm accepts the proof as valid. So we point out that the penalty style definition appears to be more useful for applications, while the exclusion style definition is less so. As a canonical application, we consider the use of NIZKs to construct digital signatures, as was first done by Bellare and Goldwasser in 1990. So the concept of dual mode proof systems was first introduced by Groth, Ostrowski, and Sahai in 2006. In this technique, there are two proof systems, pi0 and pi1. The two CRS generation algorithms here generate common reference strings, which are computationally indistinguishable from each other. Meanwhile, the proof systems have proof generation and verification algorithms, which are identical to their counterparts. What's the benefit of such a pair of proof systems? So Groth, Ostrowski, and Sahai use the perfect soundness of one mode and the computational indistinguishability of the common reference strings in order to prove the computational soundness of the other mode. This led to the construction of the first perfect zero knowledge argument system. So we now introduce the terminology of transference. As before, we have a pair of proof systems pi0 and pi1 that are dual mode proof systems. We require that the CRS generation algorithms generate CRSs that are computationally indistinguishable. If one proof system, say pi0, satisfies a property P, then we can use that along with the indistinguishability of the CRS to claim that the other proof system, that is pi1, satisfies the computational analog of the property P. We say that the property P transfers if this claim holds. So the purpose and applications of prior work depend on the transference of different properties between the modes of the proof systems. Therefore, we ask the question of which properties transfer. We look at this question for a number of different properties like zero knowledge, witness indistinguishability, extractability, and soundness. So we first define dual mode proof systems in a novel way, which has only the CRS indistinguishability requirement and no additional requirements on the individual modes. We call this requirement mode indistinguishability. We formulate the question of transference and ask which properties transfer. We prove some negative results. We show via an explicit counterexample that the SND-P notion of soundness does not transfer. We also show a separation between SND-E and SND-P notions of soundness. We then turn to positive results. We provide an abstraction of property specifications, and we state and prove a transfer theorem. This abstraction allows us to capture all the positive results simultaneously via a single proof. As a result of this theorem, we are able to show that the standard definitions of zero knowledge, witness indistinguishability, and extractability do transfer. So in the interest of time, I will focus now only on the negative result for the transference of SND-P and defer the remaining to the full talk and paper. So let's now look at the non-transference of the SND-P soundness notion. The intuition here is that this property fails to transfer because transference requires a reduction adversary to test for membership in the language. As we have mentioned, the languages of interest are in NP, which means that membership tests would be inefficient. We show that there exists a dual mode proof system and a relation such that the proof system is mode indistinguishable. One induced mode is SND-P, but the other induced mode is not SND-P. This counterexample that we show will be based on the hardness of the decisional Diffie-Hellman assumption in a group G. So the dual mode CRS generation algorithm generates the CRS in two different ways. Mode indistinguishability can be seen to follow directly from the DDH assumption in the group. We further define the relation in such a way that the language consists of all group elements except G raised to AB. We further define proof generation and verification so that in order to break soundness, all the adversary needs to do is pick the statement as G to the AB. So now when mu equals 0, we can see that the CRS itself contains G to the AB, and therefore the adversary can easily pick that value from the CRS and break soundness with probability 1. However, when mu equals 1, we show that we can reduce the soundness property SND-P to the DDH assumption in the group. So this shows that SND-P does not transfer. So here's a summary of our contributions. The main takeaway is caution while using these dual mode proof systems in applications, because the properties we require from induced proof systems might not actually have transferred. More details can be found in the full talk and in our publication on ePrint, which is report 2020/629. Thanks, and I'll be happy to take questions again.
Great, thanks for that, Vivek. Yeah, there doesn't seem to be any questions on Zulip, and we're at the sort of time where we need to hand over to the last talk. So okay. Yeah, let's hand over to the last talk.
Okay. Can you see the screen?
Yes, we can.
Okay, thank you. Thank you for your introduction. I'm Kyosuke Yamashita, a PhD student in Kyoto University, Japan. I will be talking about black box impossibility of an NIZK for secret equality. This is a joint work with my supervisors, Meditibsi and Masayuki Abe. So overall, we consider the problem of expanding a language class of NIZKs in a black box manner. So we consider this problem. Suppose we are given an NIZKs for languages L0 and L1 respectively. Then we consider if we can generally construct an NIZK for this language, in particular, which includes the witness equality. Actually, such an witness equality NIZK has a lot of applications in cryptography, such as Nawa-Young construction or contingent payment in blockchain, which guarantees a fair trade. So if we can find such a general construction, we may be able to construct these applications efficiently in the future. So this type of black box language extension work was initiated by Abe et al. in PKC 2020, and they showed some negative results on it. However, they only considered this kind of simpler languages, so the language which includes witness equality is not covered by their work. So in this work, we focused on the Nawa-Young construction and showed the following result. Suppose we are given a CPA PKE and an NIZK for the language LCPA. So this NIZK proves a ciphertext is valid and a public key. Given these primitives, we showed there is no fully black box construction of an NIZK for this language LEQ. Actually, this NIZK is used in the Nawa-Young construction, and this NIZK proves that two ciphertexts are valid and are given public keys, and they share the same plain text. Towards this goal, we first introduced an Oracle ZK, which almost directly implements an NIZK, and we showed this Oracle ZK indeed constitutes an NIZK for the language LCPA. Then we go into our main result. So first, we suppose that there exists a black box construction M of a proof system for LEQ that satisfies the zero knowledge property. Then we demonstrate an adversary that breaks the soundness of M in the standard soundness game. In the construction of our adversary, we followed the swapping technique, which is introduced in the previous work. So let me sketch the swapping technique in the next slide. This is a standard soundness game, so there is a challenger and an adversary. Both of them have Oracle access to ZK. First, the challenger generates a CRS and sends it to the adversary. And the adversary computes two ciphertexts from different plain texts M and M prime and runs the prover algorithm on this pair. Because C and C prime come from different plain texts, the prover algorithm is not supposed to output a proof, but the adversary cheats this algorithm as follows. First, suppose the adversary makes a query which includes C prime and M. This is invalid pair. An important observation is this query is actually made by the adversary, so the adversary can control the query. Then the adversary swaps the query so that it contains M prime and returns the answer to the algorithm. And if this oracle is implemented by a random injection, the prover algorithm cannot detect such a swapping and finally outputs a proof. And if this proof is accepted, then the adversary wins the game, and we showed such a probability is non-negligible. So by following the swapping technique, we showed the negative result, and this is future work. So thank you for your attention.
Thank you for the talk. Any questions for Kyosuke? I don't see anything on Zulip either, and there is nothing on the chat. So if you have questions, perhaps you can leave it on the chat either on Zoom or on Zulip. Yeah, with that, I guess we move to a break. So thank you, Kyosuke, and thank you, Vivek, for the previous talk as well.
Yeah, thank you all the session chairs. Thank you, James. Thank you, Makul. Thank you, Bhavana and Venkata. So as Bhavana announced, we'll take a short break, 13 minutes break, and come back for the invited talk.
Thank you. Bye.